We now need to check to see if the empirical formula is the same as the molecular formula. And we do this by comparing the molar mass of the compound, which is given in the problem, to what we will call the empirical formula mass. So we're going to take the empirical formula of C2H5 and find the molar mass of that. So it will be 2 times 12 grams for the 2 carbons, so 24 grams of carbon, 5 times 1 gram each for the hydrogens. So the empirical formula mass here is 29 grams. It is not the same as the molar mass of the compound, which is given as 58 grams per mole. So we have another step to do to get the molecular formula, in which we're going to compare the mass ratio and then use the mass ratio times the empirical formula to arrive at the molecular formula. So here's what finding that mass ratio looks like. We take the molar mass divided by the empirical formula mass. So we have 58 grams per mole over 29 grams per mole. That equals 2. The grams per mole cancel. Then we take that 2 and multiply it times the subscripts in the empirical formula. So 2 times C2H5 would give us C4H10, and that indeed is the molecular formula for butane. Let's try another problem. Here we have a sample of an unknown substance is analyzed and found to contain 11.04 grams of potassium, 2.92 grams of phosphorus, and 6.04 grams of oxygen. We want to determine the empirical formula of the compound. Now, short note here, this compound contains a metal, meaning it's an ionic compound. The empirical formula of this is the formula of the compound. This is not one that you'll be doing any type of ratio of molar mass to empirical formula mass, simply because with ionic compounds, that simplest whole number ratio of ions in the compound is the formula for the compound. It's not the same as a molecular compound in that sense. Now, when approaching all empirical molecular formula problems, we should keep the poem in mind: percent to mass, mass to mole, divide by small, multiply to a whole. Here, however, you're given the masses up front and not a percentage, so you can skip this step. Since we have the mass, you can go right to the mass to mole step. Here are our mass to mole conversions. Again, we do this as we've done them before. So when we do these calculations, we find that we get 0.2824 moles of potassium, 0.0943 moles of phosphorus, and 0.3775 moles of oxygen. Once we've determined the number of moles in each of the compounds, or in each of the elements that are in the compound, we can then go to the next step, which is finding the mole ratio. So here are our mole ratios. Again, taking each of the mole quantities and dividing by the smallest mole quantity. So our mole ratio is that we get 3 moles of potassium for every 1 mole of phosphorus and every 4 moles of oxygen. The mole ratios here are whole numbers, so we can go ahead and write the empirical formula, which is K3PO4. There is no need to multiply to a whole, and you should find this true of all ionic compounds for reasons that we discussed previously. So the answer to this is potassium phosphate, and the formula of the compound, which is the same as its empirical formula, is K3PO4. Well, it's time for your turn. I'm going to give you some sample problems to do. We'll call them your turn problems, and what I'd like you to do is to pause the podcast, write the problem down, solve the problem, and then resume the podcast, and we'll look at the answers. Hopefully yours will match up with mine, and we'll see how you do. So go ahead and pause the podcast and go after these. Our first problem, we're going to determine the percent composition for each element in aluminum chromate, which is Al2, then in parentheses CrO4, 3. Welcome back. Let's see how you did. The solution is going to be on a series of slides that you'll be watching. So if you need to pause the slides to write things down as you compare your answer to mine, that would be a wonderful thing to do. The first thing here is to find the molar mass of aluminum chromate, which is shown here. The method that we use to find molar mass allows us to see the mass of each individual element in the compound, which makes it very easy then to calculate the percents. So you can see here we take the 54 grams of aluminum over the molar mass, which is 402 grams of aluminum chromate, multiply that by 100 and we get 13.4% aluminum. We do the same for the mass of the chromium and the mass of the oxygen compared to the overall molar mass of the compound, and we end up with 38.8% chromium and 47.8% oxygen. When we add those percents together, they come to 100%, which it should, and if it doesn't, that's a good sign that you need to go back and identify where you may have made a mistake, either in determining the molar mass or the mass of the individual elements in the compound. This is the end of part 2 of the video podcast series here at Ontario High School, dealing with empirical and molecular formulas and percent composition. I want to leave you with a quote from Charlie Sheen. As kids, we're not taught how to deal with success. We're taught how to deal with failure. If at first you don't succeed, try again. If at first you succeed, then what? Stay tuned for part 3. I wish you well.